Hi, this is Miss Litton, and these are my wonderful AP biologists. Say hi. Hi. And we are here for a review over Chapter 6, Metabolism, Energy, and Enzymes. So the first thing I would want to know is make sure you kind of have an idea about kinetic energy as energy of movement, and there's thermal energy, so all different types of energy. I know the laws of thermodynamics. I have them in my head. So the first law says that energy is not or destroyed. It can just to be transformed. The second law says every time it's transformed, you lose some as heat. You don't get 100% transformation. We good? Okay. Then we looked at some examples of that. Dun, 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 dun. Then we started talking about entropy. And entropy, if you have high entropy, you have a lot of mess, a lot of disorder. And the whole reason we do cellular respiration is to make what? Thank you. To make ATP, and ATP gives us energy so that we can maintain and not fall apart. Because everything wants to go to greater and greater disorder. Okay, and that would be entropy. So we're trying to always fight it. The thing about entropy, though, is it's very what? Stable. I was trying to be stable. It's very stable. Does it have very much potential energy? No, not a lot of potential energy. And we said something like this is very clean, but that is not as stable because just one thing can put it out of place. Okay, but let's leave kitchens and let's talk molecules. So we talked about the difference between glucose and carbon dioxide and water. And you know, because we already learned the end of the chapter, that glucose is a starts with an R. Glucose is a reactant for what? Cellular respiration. Glucose is a reactant for cellular respiration, and a product would be carbon dioxide and water. And glucose has a lot of potential energy because when you hook all those carbons and hydrogens and oxygens together, they have what to hold them together? Covalent bonds. Yeah. And so when we break those covalent bonds down, we can harvest energy from that. So carbon dioxide and water has more entropy but less energy, right? More entropy but less potential energy. And then we apply that, which we learned also and came back and visited at the end of our little presentation. When you concentrate hydrogen ions on one side of a membrane, or anything on one side, could be sodium ions, could be potassium ions. When you concentrate something on one side of a membrane, that has a lot of what kind of energy? Starts with a P. Potential energy. Because those molecules, in this case hydrogen, want to go from a higher concentration to a lower concentration. And when you see this difference, this differential right here, there are more hydrogens on this side and there are fewer hydrogens on that side. So there's a difference in concentration. But there's also a difference in concentration, but what else is there a difference in? Hydrogen ions. There's a difference in what? Charge. Okay, and there's a difference in pH. Okay, and when we look at that, that's called a chemiosmotic gradient. Okay, there's a difference, such a great difference on either side. The hydrogen is super motivated. The hydrogen is super motivated to move from one side to another side. And remember how we talked about coupled reactions? What do you remember about coupled? An exergonic reaction, one that releases energy, can drive a endergonic reaction, one that needs energy. So these hydrogens want to go to that other side, and you couple that with the production of ATP. How? Because they're so motivated to go through that they go through ATP synthase complex, right? And that's the little turnstile that we're going to learn about in the next couple chapters. And remember we talked about like people wanting to go into Disneyland when it opens. People are super motivated. Or clearance, if you're an athlete, when you have to get in line, you're super motivated. And so you go through that turnstile, and when you go through that turnstile, that snaps a phosphate onto ADP, making ATP. So you've coupled that chemiosmotic gradient with the synthesis of ATP. turn to the person next to you and go, anything on there in the Shadowlands for you, or are you sunshine? Any Shadowlands? Look at the sun. Look at a light. Go look at the light. All right. Now, should you memorize? Would you memorize carbon dioxide as what? Low or high entropy? What we talked about. What is it? High?
Oh, wait, low.
Low?
Hi.
Okay, now.
Oh, wait, it is high.
Ah, okay. So, hear me. Do not be small-minded. Small-minded person is like, oh, I'm going to memorize carbon dioxide, high entropy. That's not what you want to memorize, okay? You want to have an understanding of the big picture of energy. Things that are more complicated, concentrated, more bonds, that has more potential energy, and the opposite of having potential energy is usually having a lot of entropy, right? Those are opposite. Entropy is disorder, okay? Does your room have high disorder right now, your bedroom, or low disorder? Is your bed made? Is your desk neat? Are your clothes put away? Are there clothes on the floor? What's your bathroom look like? Okay, if you could give, generally speaking, you know, there might be that once in a blue moon, like once a quarter you clean your room. Okay, but generally speaking, what would you give yourself as an entropy rating on a 1 to 10 of your bedroom? And if that can help you remember about entropy being disorder. You know, 10 being a lot of disorder, 1 being highly ordered. Quality seat. Yes. Wait, I can't hear. I can't hear still. No, it wasn't your fault, it was their fault. Go ahead.
Carbon dioxide molecules make carbohydrates, right?
Yes, in photosynthesis, an endergonic reaction, you can reduce CO2 into glucose. Yeah, using reduced NADP and ATP along the way that you make in the light reaction. Yeah. Go.
So if you have more bonds and they're more complex, then do you have a higher potential energy
Yes.
for lower entropy?
Yes. There you go. Boom shakalaka. Own it. Own it.
I did. I pulled up.
Yeah, see? I didn't hear what you just said, but I'm sure it was really good. What about glucose? Where are we going to put this?
Lower.
Okay. But does that make sense to you?
Yes.
Okay. Okay, make it make sense. Entropy. 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 Just what I did. I was trying to think like your entrails, pee disorder. Somebody peed all over your room, that'd be a lot of disorder. I'm so glad I'm recording that. I'm super tired. I didn't get enough sleep last night. Okay. All right, we got that? Good. All right. So this does not change. The entropy of the universe, it's always increasing. Everything's going to greater and greater disorder. But as our sun is going to greater disorder, it's releasing energy, right? And we use that energy to organize us, to fight entropy. Okay, but eventually it's going to run out. All right. Okay, entropy, disorder, yes. Hey, I see a question in here. Be your first pet. Be your first pet. Yes, sir. High potential energy. Potential energy. Free energy. Okay, are you in? Grab the I'm showing questions. Here's number 1.
There's no diagram.
Oh yeah, remember we've had this discussion before. I'll draw you one.
Everyone put true.
I was gonna draw you one. Oh, the answer is
The answer is false, I think.
yeah, I meant to put that out. Yay! Period 4 right now stands at 7 100s in a row, and they are a ... They can get even still more. Oh my gosh! Oh, shame. The first, come back to me. I know you're going to greater and greater entropy. I'm trying to fight that. Okay, stay with me. Okay, stay with me, Mr. Parker. Okay, so sorry, you have to watch news. You know there's something. The first law says energy cannot be what? Created or destroyed, but it can change, right? But that change, that transformation in law 2 says that it's not going to be 100% efficient. All right. Next. Stay with me, Mr. Parker. Okay, so metabolism is all your enzyme-mediated reactions. Now, when I say that, because you've learned so much more about enzymes, all your enzyme-mediated reactions. Okay, these are reactions that are controlled in some way by a what? Enzyme, right? There's 2 types. Anabolic reactions, which are about building. And to me, whenever I hear the words, I'm going to build something, I'm going to assume that's going to require some energy. Okay? You're going to have an input of energy. And a catabolic reaction is about breaking. I'm assuming it's going to what energy? Release energy. Good. Okay? And then when we talked about coupled reactions, this would be a good example of a coupled reaction as well here. A catabolic reaction that releases energy that's exergonic, that energy can be used by an anabolic reaction, an endergonic reaction. Will this be 100% efficient?
No.
No, what law says that? Second law. Okay? Okay, the second law would say that. In this case, these are what would you refer to both of these as? Starts with an R. Reactants, and this would be a product. And to get any real amount of product, any large amount of product, because I said this is your metabolism, these reactions would have to be mediated by an enzyme. Okay? So your metabolism is all of these reactions, the sum total of all of those reactions. Okay, so we talked about reactants and we talked about products, and then we got to delta G. Remember that? Energy available to do work. And then we got, I'm skipping ahead. I was going to say it gives free energy. But this one is exergonic releasing energy, and this one is endergonic requiring energy. You don't have a problem with that, right? Easy peasy? Okay. So then we get to Gibbs free energy equation. Okay? So when we look at this equation, how do you count? When I say delta G is this, right? That the delta G got negative or the delta G got positive. When you hear delta G is negative, what does that mean? What happened to my energy? If I just say, don't even look at the board, just make it logical. Delta G is negative. What has happened? I lost free energy, right? I lost it because I went negative, right? I lost free energy. So therefore, the reaction must have been what? Exergonic. If I lost it, I must have released it, right? Nobody stole it out of my hands. I released it. It's exergonic. If my delta G is positive, if I have more free energy in my products, then that reaction must have been what? Endergonic, right? I must have done something to organize it more. right, to have a positive delta G. I must have been something to organize it more. So now when we look at these different parts of it, change in enthalpy, that's like the energy measurement at that time. Don't stress out about that. But delta S is a change in entropy. Are we going to more disorder or less disorder? Right? So if I have an endergonic reaction, I put energy into it, I'm probably going to more, what? Order or disorder? Going to more order. What do we know about order? We know then that the entropy, the S, the entropy must have been small. So see how my delta G will probably be a positive number? But if I'm going to greater disorder, if I'm exergonic and I'm releasing and I'm breaking down, then my disorder must be high, right? A lot of disorder. So my delta S would be what? Big. So therefore, since I'm subtracting that off the total change in enthalpy right here, then I'm probably going to have a negative number. So if you focus right here, right, and temperature is going to speed up. Whatever I'm doing, I'm going to do more of it if it's hotter, and I'm going to do less of it if it's colder, right? It's like stepping on the gas hard as opposed to just a little bit, right? Whatever you're going to do, you're going to do more of it if the temperature is hotter. So this number right here, this is saying what's the energy I have? Am I subtracting off a small number of disorder, or am I getting a big disorder? If it's big disorder, a number minus a big disorder is always going to go negative. That's going to, my delta G will be negative, right? But if I'm going to greater order, my delta S would be very small because my entropy is not going to be a big, I'm going to have less of that entropy. So if you think about it like that, then that equation probably won't freak you out. Okay, hopefully. Okay, and that, yeah, hopefully. Does anybody want to ask me questions about that?
What do we have to know about the enthalpy?
What?
Or enthalpy. And how do you say it?
Enthalpy. So this is the total energy for this system. So your whole system. Don't stress out about it. It's like saying so free energy is energy available to do work that I can do something with. So this is energy of the entire system, and this is energy available to do work I can do something with, right? Because if I do this, right, I'm releasing heat out into there. I can't really do anything with that, but it's part of the energy of that system, but I can't do anything with it anymore. It's not available to do work. Okay? Did I see another? Yes?
Do we need to know how to solve a problem for the quiz, or is it just understanding the equation?
Let's just worry about understanding the equation for now. I did not put a calculator question on your quiz. Does that make you feel better? There's no need for a calculator question on your quiz. Breathe easy, young Padawans. Yeah, just understanding it. Okay. Oh, we've already done this. Do you want?
We do it again?
Okay. Do you want to do it right now? Okay. It should come to you. It should have come to you now. I'm going to pause this. Hey, can I get a couple people to come up here and do it on the board so that it's recorded in here? I don't need to do it. Somebody, come on, be brave, young Padawans. Who wants to do it on the board? Come on. Nobody. Okay, I'm going to pause this. You'll be fine. Let's do a bunch of them. Okay, come do one.
I have to make sure that you find it.
Take you over here.
Be ready to give me one, and I'll move them for you, or he'll move them for you. Come on up. You're the he. Okay, he got. Okay, yeah, he did exergonic reaction, and what does it say? Free energy. I can't read it because it's too small. Free energy decreases. Good. Give me another one that you know you got right, and I'll do it up here on the board so you have it for review. Entropy as increases. If entropy, what do you want to say? If entropy decreases. What? More disorder. Good job. What's another one? Do another one for me.
T decreases in lower temperature.
what T decreases.
And then lower temperature.
All right, good one. Lower temperature. Whoa, whoa. Did we not get that?
Endergonic reaction.
Oh, I got T increases. Sorry, let me fix that. Higher temperature. There we go. T decreases. Where's lower? Here we go. Sorry. There we go. I grabbed the wrong one. What else? What else? Delta G is positive.
So
H increases and S decreases. Yeah. Okay, what's another one?
delta G is negative.
Good job.
What is it? H decreases and S increases.
Perfect. Give me another one.
H increases.
Okay, H increases. Good job. What else? H decreases maybe? Total energy decreases. Good job. What else? Endergonic reaction is what?
Free energy is increased.
Free energy is increased. And entropy S decreases. Less disorder. Yay! Good job. All right. Okay. The next thing we talked about was what makes our cells go? What's the energy currency of our cells? And we said it's ATP. And we reviewed the structure: adenosine triphosphate, adenine, a purine, a nitrogenous base, right? And ribose, and then 3-phosphate. And notice what we're doing right here. We're adding in water. So what kind of reaction is this? Hydrolysis, hydrolysis. Okay, and we're releasing energy. We then talked about the coupling of anabolic and catabolic reactions, but we have already discussed that. Ask your bio buddy, Shadowlands or Sunshine here? Okay, come back to me. Go. Quiet. Yes, no problem.
I know, like, we know what, like, a catabolist reaction versus an anabolist reaction is, but we don't know, like, what's it coupled to, like, what exactly is it coupled together?
Okay, so maybe I want to move my muscles. That is going to require ATP, right? So I'm going to couple that with the hydrolysis of ATP with the ability to move my muscles. I'm coupling those together. So that's releasing that energy, and this one is requiring energy. You just do it all the time. Everything is a payoff. Nothing's free.
So it's the exergonic with an endogonic.
Every time. Nothing's free. Exactly. Nothing's free. Because if a ball rolls downhill, somebody had to put it up on the hill. Okay? All right. So here is a coupling of a reaction. Okay, and we did that, Okay, so glucose, right? We said it's more complex because of all of those bonds between the carbons and other carbons and hydrogens and oxygen. And if you cash out a $100 bill aerobically, doing aerobic respiration, when you turn in your $100 bill to the cellular respiration machine with oxygen, you'll get $39 back. If you turn in your $100 bill anaerobically without oxygen, you'll get $2 back on your $100 investment. Doesn't sound good to me. Okay, we have to, in order for us to survive as multicellular, we got to at least get $39 for our $100. We can't survive without oxygen. And why? Because there's an electron transport chain, for us in our mighty mitochondria. And remember how we had the electrons moving, and then they would move a hydrogen ion from one side of the membrane to the other side of the membrane, and the final electron acceptor at the bottom of the chain was oxygen. So we need it as our final electron acceptor when we think about being reduced and oxidized, and we'll hit that again in our next 2 chapters. But anyway, why do we need ATP? It falls under 3 big categories. Chemical work, if you're going to do any endergonic reactions where you need to synthesize something, transport work across a membrane, and mechanical work like muscle contractions or movement of a cytoskeleton, flagella, etc. Okay, and here is a question for you. somebody had a dog named Ravioli? Or was it a cat? Was it a fish? It should be easy peasy. You should be blowing through this question. Another easy peasy. Oh yeah, this was a weird one. Yes.
So, again, back to coupling reaction.
Yes.
Yeah, would that work with, like, in the textbook, there was, like, a model of actin and myosin? We need to fix that.
Actin and myosin, sliding filamentary for muscles, yes.
Is that, like,
Well, yes, because you need ATP to move the tropomyosin to this opponent so that the myosin heads combine onto the actin and slide past one another. So to get that muscle to contract, you've got to have ATP.
oh, okay.
All right, I'm ending this. Let's see how we did. Excellent. Excellent, that's 2. So, the 10 of you who missed this, you all said either A, B, or C was correct, but the actual answer is D. Right? All of those are true. ATP becomes ADP plus phosphate. ATP is hydrolyzed, it's broken down if ATP is coupled with an endergonic reaction. All of those are true. Yes? Got it? Okay. So now we talked about what metabolism is, but bigger still are metabolic pathways. This triggers this, triggers this, triggers this, triggers this, and they are all usually catalyzed by a specific enzyme. There's an enzyme for every one of these reactions. So we started talking about enzymes, and what enzymes have is they have an active site, and the active site is where the substrate binds to the enzyme, right? That active site. And those active sites, because enzymes are proteins, what do we always know about proteins? They're very what? Specific. So when the active site binds onto the enzyme, at that point, when you have an enzyme substrate complex, it might actually change its shape a little bit. What's that hypothesis when it changes its shape to get a better bind? Induced fit. Boom shakalaka. Induced fit hypothesis, where it changes slightly, and then as a result of that, then you have your product. Now, this is a reaction where you're breaking something down, right? In this one, and we talked about there could be, and here's some induced fit. We said you only need a little bit of enzyme because it's not consumed by the reaction. Like glucose is consumed by cellular respiration. When it's glucose coming in, it's carbon dioxide and water coming out. It's consumed by the process. An enzyme that you use along the way, that's just going to be used and reused and reused and reused. Okay, so you only need a small amount. And we talked about how enzymes are named after their substrate. Now, endergonic reactions, it makes sense. An endergonic reaction is going to require the input of energy, and it could, party on my wrist. I'm at my step goal for the day. The endergonic reactions for sure. That's like you're here and you need to be here. That's going to require energy. That's going to require an enzyme. But you would think if you're starting up high and you're coming down low, a catabolic reaction, an exergonic reaction, you would think those would just happen all the time. Well, that would mean you and I would just fall apart all the time. So there's a little hurdle that prevents that. That little hurdle is called the activation energy, or energy of activation. Okay, it prevents spontaneous reactions from happening all the time. It keeps you all together, keeps you complex. And you need an enzyme. Now, heat a lot of times could lower that, but heat will lower every reaction in your body, make it more likely to occur. Whereas an enzyme specifically lowers it, so instead of your hurdle being here, your hurdle is here, and kinetic energy is enough to overcome to make that reaction go forward. So this is without the enzyme, and then the energy of activation is lower with the enzyme. And remember how much faster can it make that reaction go? You remember? 100 million times faster? Do you remember? 10,000 times faster?
No, 10 million.
10 million times faster? What was it? So, you could, this hydrogen peroxide that you had in your lab where, you did the dry, you tried it. When you did the run of that, okay, it could break down into oxygen and water spontaneously, just very slowly. A very small amount would occur. It's more likely to occur. You can see those bubbles right away when you have catalase. We talked about that reactants, depending on the enzymes are specific to the reactants, but you could have one reactant, but you could take it down several different pathways depending on what enzyme is present, right? The same reactant could go several different pathways depending on what enzyme is present. All right, and then let's move on here. We've talked, here, let me ask you this. I think this is the question I don't like. Possibly. We'll give it a go. Okay, just in case they've left. So, how did you know the reaction was exergonic? Energy's on the product side. Product side. If it's on the product side, then it's going to be exergonic. Can an enzyme speed up reactions? Yes. ATP is not needed. Does it say anything about ATP having to be coupled with this reaction? No. A and B are reactants, C and D are products. Yes. So then we said, what are all the factors that can affect enzyme activity? See if you can think of a bunch of factors in your head right now. Factors. Give me one. pH, temperature, substrate concentration, enzyme concentration, cofactors, coenzymes. We got substrate concentration. I'm looking for one art. Inhibitors. I can't hear you. Oh, I know it. Phosphorylation. There we go. All right. What is she thinking? I know she's thinking something. Okay. So, yes, if you increase the substrate, you're going to increase the amount of product you have up to a point. What is the up to the point? What is the point?
Point of saturation.
Point of saturation on what? On what? What does the substrate bind to? If all the active sites are consumed, you can't go any faster than that. Right? Okay, because it's working as fast as it possibly can. It's at maximum operation. If you added more enzyme to it, could you get more product? Yes. But this is why it levels off. This is the kind of thing they would like to ask you. Why is it leveling off? It's not like it got denatured and too hot of a temperature, right? It just leveled out. It maximized at this particular amount because all of the active sites were occupied by substrate at that point. Okay, 2 different pHs. Optimal, where they have their optimum performance, is going to be at a specific pH. Same thing at a specific temperature. Yeah. We talked about cofactors. Cofactor could be anything that helps an enzyme function, but a coenzyme is a cofactor that is what? Organic. Would you say a coenzyme could be a protein? If it was a protein, it'd just be part of the enzyme, because enzymes are proteins, right? Okay. Hello.
Hi. Is your class still going?
It is.
Alright, I'll stop by in a minute.
Okay, I know you.
Yeah.
How are you?
I'm good.
Oh my gosh. When did you graduate?
College or high school?
Gosh. Let's start with high school.
2012.
Oh my gosh. Okay, yeah, we'll be done here in just a little bit. Okay. They're so flippin' old these days. It's really terrifying. What's worse is when they come in with their 16-year-old children. Yes.
So the cofactor helps create, like,
A cofactor is kind of like something that makes the enzyme functional. It's like hemoglobin needs iron.
okay.
You have anemia or an iron deficiency, then hemoglobin's not going to work because that helps it change its allosteric shape, its conformation usually.
So it's required for the enzyme.
Enzyme to function at maximum potential.
At maximum.
Yeah,
But then-
like oftentimes vitamins are coenzymes.
I think we're good, Erin. We're good.
Wait, stop. Shh. Go. I'm listening.
But if you have a coenzyme, does it inhibit the, or is a coenzyme and a cofactor essentially the same thing?
Cofactor would encompass coenzymes under the same umbrella,
Okay.
but a coenzyme is an organic cofactor.
Okay.
Does that make sense?
Yeah.
Okay. Okay, let me get this last bit out to you. We talked about, oh, there's a coenzyme for you. Your inhibitors, okay? If you're a competitive inhibitor, you're competing with the enzyme for the what? Active site. If you're a non-competitive inhibitor, you bind somewhere else, but it affects the active site. Okay? The last thing you really want to get in your head, reduced and oxidized. If you're reduced, you have more electrons, more energy, but you're called reduced because you have a lower charge. What are the 2 ways to get reduced? Hook up with hydrogen or break up with oxygen. Either way, you're going to have more energy. Okay? And oxidized is the reverse of that. So you might want to review that. And then the linking between cellular respiration and photosynthesis. Review that as well. Okay? Oxidized, reduced.